Hi, I'm Katie Milliken. Welcome to the Utah Energy Code podcast, Getting Up to Code, Energy Talks with Brent Ursenbach. I just want to take a moment to thank our partners, the Utah Governor's Office of Energy and Development, Rocky Mountain Power, Dominion Energy, and DOE. And welcome to episode 1, the science behind the Energy Code. What is the science behind the Energy Code? Why is it important? Isn't it simple? Install a furnace to keep us warm in the winter and an air conditioner to keep us cool in the summer. Why is all this code and science stuff important?
Thanks, Katie. Appreciate the opportunity to be here. Why is all this science stuff important? Many of us do think that simply putting in a furnace and an air conditioner, maybe put in a big one so we're sure it's going to do the job, is all we need to do. But there is a lot of building science that we need to be considering if we want our buildings to be healthy, safe, durable, and a lot of other features, and of course, energy efficient. So building science, our introduction. Building design and construction and operation can affect occupants' health, occupant comfort, building energy consumption, building structural durability, and that's a big one. We've heard lots of instances on the news lately where there have been lawsuits and litigation over water intrusion issues into our buildings, and so that's an important thing to consider. The building envelope separates conditioned space from unconditioned space. So as we look at this home that we have right here, if we consider the garage typically is not conditioned, but the rest of the home is conditioned. So any components that separate the conditioned from the unconditioned space is considered a component of the building thermal envelope. I want you to be aware that this podcast will discuss the science. The code is currently discussed on UtahEnergyCode.com website with many of our productions, training sessions and stuff recorded there with lots of resources there, so remember to go to that slide. As I said, we'll just discuss the building science in this presentation, and then coming up we will have future podcasts that maybe will go into a little depth on some of these subjects. So we have 3 areas of envelope focus. The first is airflow. The second is heat flow. And the third is moisture flow. Now remember, as we talk in this podcast, we're talking airflow, heat, and moisture flow through the building envelope. We're not talking about airflow through the HVAC system. We're talking it through the building envelope. Each impacts the other 2. So we can't just look at the airflow and say everything in airflow stands alone, because the airflow will impact the moisture flow, as will the heat flow. So they're all integrated to create a good building envelope. Future energy talks on the Energy Code will also hit HVAC, ventilation systems, testing, and much more.
So would you consider a basement to be inside the thermal envelope, or what about a bonus room over the garage?
Good question, Katie. The building thermal envelope, let me read this definition and then we'll talk a little bit about your question. The basement walls, exterior walls, floors, ceilings, roofs, and other building element assemblies that enclose conditioned space. So let's talk about that basement. In fact, let's read a little bit further. Or provide a boundary between conditioned space and an exempt or unconditioned space. So if we have a basement and we insulate the floor above the ceiling of the basement or the floor of the main floor above, then we're creating an insulated boundary, and so the thermal envelope would be the space above the basement. However, if we insulate the basement walls, then we are creating the boundary down to the basement floor. And so the basement can be conditioned or unconditioned depending on how we insulate that or where we create that building envelope. Same thing will go for other things like the bonus room over the garage. The garage is not conditioned. The bonus room is over the garage. We have an insulated floor under the bonus room or ceiling of the garage, and then all the walls around it. And that brings up a really good point. That bonus room over the garage is exposed to unconditioned space virtually on all sides except for maybe a connecting hall coming from the rest of the house. So what's it going to be? It's either going to be colder or hotter because it's more exposed to the outdoor condition, where the rest of the house might have just one or two walls exposed and a ceiling. So that boundary is the thing that we need to be thinking about. And that boundary is a really important thing as we look at the airflow and the moisture flow too, because it's really that separation between conditioned and unconditioned space. So this is an analogy I like to use when we're talking about building energy efficiency. Most of you out there that will be watching this, and Katie, I imagine you're familiar with these high efficiency coolers, these super expensive, super insulated coolers.
They are not cheap.
No, they are not cheap. My wife and I have spent quite a bit of time during this COVID thing taking the trailer up in the canyons above Camas and doing some camping. And about every 2 days, I have to go down and get some more ice because my cheap cooler melts all the ice away and I'm running out of ice. And I'm trying to build up the desire to buy one of these, and I probably will. But these coolers keep food and drinks cold 5 times longer than standard cheap coolers. So my cooler that keeps stuff cold, keeps the heat out, will go 10 or 11 days rather than 2 days. Simply by reducing the amount of heat transfer either into or out of the cooler. So the cooler will also work if you put warm food in it. It'll keep it warm for a long time. And how does it do it? It does it by increased insulation. So the walls of this cooler and the lid are better insulated. And you'll see that there's a hard plastic shell all the way around, then it has spray foam injected in it. So it's really tightly well insulated with a high R value, much, much more than we see on my cheap little cooler. So we have less conduction, or we have less heat flow. Now, what are we worrying about in our cooler? We're worrying about the heat getting in. In our home, we're worrying about heat getting out in the winter or heat getting in the summer. So it really doesn't matter if we're talking about summer or winter. We either want to maintain the heat within the home or within the cooler, or we're going to stop the heat from getting into our home in the summer or getting into our cooler when we're using it to keep stuff cold. The other thing that you'll notice on these coolers versus my little cheap one, and I won't say the brand, is that they have a gasket that seals. And you even see there's a little ridge that sticks up and makes sure it compresses that gasket tightly. And so we have no air leakage in or out of the cooler. Mm-hmm. The only time you get air in it is when you open the lid, and then you're going to get some warm air in, just like our home. If we have a well-insulated, well-sealed home, we don't get a lot of air transfer in and out unless we're opening a door or a window. And so by having it air sealed, we have less convection or airflow between inside and out. Now, the problem with a cooler, we couldn't live very well in that type of thing because we wouldn't have any fresh air. Yeah. So fresh air is not an issue on our Yeti cooler, but the concept of the insulation, the air sealing, we can take and directly apply to our homes and our buildings. So, we could talk about, I want to build my structure like a Yeti cooler or a Pelican cooler or whatever brand. They all use the same type of technology, good insulation and air sealing. So those are two real important factors that we have to consider when we're looking at the building science. And by doing that, we we really have a cooler that saves a lot of energy. I'm not having to put so much ice into it. Now, if I build that super insulated house, am I going to need a furnace? Am I going to need an air conditioner? I mean, I get that question quite a bit. If I super insulate my house, I don't even need a furnace or air conditioner. And I experienced this when I was an HVAC contractor. We'd work on a house that was a really good house. They sprayed foam. They did lots of things on the house. And they would come in the summertime and they'd say, this house stays so cool. It doesn't get hot. I don't think we're going to need an air conditioner. And then I'd say, well, I think you will. And this is not something we're going to spend a lot of time on. But once we finish that house and we build our house like a Yeti cooler, then we live in the house. And then what happens in the summertime? We plug in a refrigerator, we cook, we breathe, we shower, we have TVs, and we have all these things hot air that we're creating. And so, we can build a super insulated house and we think we're not going to need an air conditioner, but we're going to need an air conditioner because we create heat by living in the house.
Yeah, by moving around.
Moving around, our body gives off heat, and just living in the house, our electronic devices give off heat and all those things. So it's not as simple as the cooler, but that's a good way to think of it. Wintertime, if you super insulate that house, you might have a condition where you need very, very little heat. And why is that? Because you are still creating heat inside the house while you're living in it. Mm-hmm. And so we are seeing with better and better insulated houses, the furnaces are getting smaller and smaller, more than the air conditioners are getting smaller, simply because we have so much technology in our house that creates heat. So the thermal envelope consists of the following, and let's just go down through the list. Fenestration. Fenestration is our windows and our doors. It's any opening that we put in our building envelope. So that's what we call fenestration. That's how it's defined. Our ceilings. So if we look at this, here's a ceiling area in this house. This is a ceiling area. We have a ceiling area here, and we have a little ceiling area here. So this is the ceiling for this space as it is for this space. Then we look at our walls. We have several types of walls. We have our above grade walls. So this one and this one and this one. And this is actually considered a wall too. Here, our below grade walls, our basement walls. So they're below grade. A mass wall would be a concrete wall. We don't have, so we could kind of call our basement walls a mass wall, but if we use concrete all the way up, then we consider it a mass wall above grade. Okay. Our floors, so we have 2 floors, 3 floors actually. We have this floor and this floor, but they're not part of a thermal boundary, right?
Right.
But this floor over here is over an unconditioned space. And this floor is over the ground. Now it's not as cold as outside, but it's still a floor that's not inside the thermal envelope. Mm-hmm. The energy code really doesn't require any special insulation in this area. But when we do load calculations, we think a little bit about this floor, because what is it below? It's maybe 50, 55 degrees, where we want 70 or 75 degrees up above. So we do have that floor that we need to consider. Now, I think you had a question on the attics or something.
So we hear a lot of discussion on unconditioned attics and conditioned crawl spaces. Can you explain how that would work looking at this graphic right here?
Sure. So let's start with the attic. And actually, I don't like the way that I have it described here. I would prefer that we insulate down here and that way, which means what? This space is inside the thermal envelope.
Yeah. And why would you do it that way?
Because we think about it, every time we put in corners and such, we impact how we need to seal the insulation. And we're going to get in this a little bit deeper as we move on. But insulation, the typical insulation we use in our homes is a fiberglass bat or a blown fiberglass material. So if we have fiberglass bat right here in this, creating that thermal boundary, then we have to put a block in here and somehow seal that space. If we don't, then we have the ability for air to move back and forth, and if we move air through insulation, we lose our value. Same thing, big thing on this one, we like to see insulation, fiberglass insulation, or cellulose, anything that relies on air within the insulation. For some of it's our value, we want to see it enclosed on all 6 sides. And what I mean by all 6 sides is if we insulate this wall, it's going to be enclosed on the face of the drywall, right here. It's going to be enclosed by the bottom plate of the wall, and then there's another plate on top that'll enclose it. The 2 studs on either side, so we enclose it there. But what happens is the back side, we typically don't have anything covering that insulation. So we have this fiberglass sitting in a wall, and it's exposed to the cold attic. So what's going to happen is the drywall will warm the air that's right against the backside of the drywall. And when you warm air, what does it do? It rises. Mm-hmm. And so we'll have air rising on the face, the inside of that wall cavity. So as air rises, what's going to happen? Other air has to come in. So we actually get a convective flow where air will flow up and around within the insulation that's in that wall cavity. And when it flows up and it pulls in air from the attic, what is it? It's cold air. Mm. And so we destroy some of the R value of the insulation by having air convecting up and down through it. So what the code wants us to do, and what building science tells us to do, is to put an air barrier or something on the back side of that knee wall so that we enclose the insulation on all 6 sides so we don't have any airflow. So if we insulate here and here, we would need to cover the insulation there. We need to cover the insulation there, but we eliminate this area here. And we give us, actually, you could put cabinet fronts here and use that for storage space and not create a void in that thermal envelope. So you could put ductwork in there. The ductwork's not outside the envelope. You could do lots of things that make it a better application, and you don't have to do all this blocking and stuff in other places. Now, when we get down to the crawl space, we can do the same thing. We can come down and put a good vapor barrier on the ground. The code's not going to worry about the ground because it's not cold. It's 55 degrees, like we said, but they'll require this to be insulated. The issue with crawl spaces, though, conditioned crawl spaces, is we have moisture coming up out of the ground.
That makes sense.
And that's an issue, So you need a real good vapor barrier on the ground to stop the moisture coming up. Otherwise, you end up with that excess moisture in your house, and then we have lots of problems when we get excess mold and everything else. And I actually have a picture of mold from a crawl space.
Oh.
So we'll see that, and it's that very issue. So I'm not real excited about conditioned crawl spaces, but I am about conditioned attics if they're done correctly. So let's just finish going down through our list there. We have the floors, our slab floor. We have our crawl space. Considering insulation and an air barrier on one or hopefully both sides of the insulation, followed by what happens to moisture within the envelope. So as we just talked about, we're thinking about the insulation and we're thinking about the air barrier on hopefully both sides of the insulation, followed by whatever happens to moisture within the envelope. So two things that we're looking on this envelope that are big things is the insulation, the air barrier, and then the moisture. And we just talked about what happens on the moisture here.
So, alluding to what we just talked about, can a building be too tight?
Great question. And actually, I'm going to say yes, a building can be too tight if we don't apply the proper building science principles. And we've had a lot of examples, and I have some slides in here that will talk about this. But back in the 70s, there was a number of items put in the code when energy first became an issue. You don't remember, but we had the first initial energy crisis, and gasoline went from 33 cents a gallon to like $1 a gallon. Mm-hmm. Now, $1 a gallon would be great today, but when the price of gas tripled in just a couple of months, that was, that really got everybody's attention, because, your fuel expenditure went way, way up. And we did have a general energy crisis. And we did a lot of things that in hindsight turned out to be kind of dumb. And basically one of the things first thing was, okay, turn your thermostats down to 68 or 65 degrees. And everybody was supposed to freeze in the winter, and then turn your air conditioner up to 80 or 82 degrees. So you had to be hot in the summertime. And people don't want that.
I remember those days.
Yeah, and it carried on. You know what I mean? And me personally, having spent more than 3 decades in HVAC, my goal was to make people comfortable. And I think we can be comfortable and conserve energy. How? By doing more than just throwing in whatever furnace and whatever air conditioner. We apply building science principles, and we build an efficient envelope. We make it tight. We control the moisture. We do all those things that we're talking about today. But we have to do all of them. And if we don't do everything, we have to do some ventilation. We have to do a whole bunch of different things to get it right. And so I said we could build a building too tight, but what I really want to say is, no, we can build a building as tight as we want. We can build it as tight as that Yeti cooler, but we just need to ventilate it, which means we have to bring a little bit of outside air, and we have to exhaust a little bit of air so that we maintain air quality. But we can control that, and just the right amount of air to maintain air quality, and not excess air, which wastes energy. So, to have airflow, when we're talking airflow again through the thermal envelope, to have airflow through that envelope, we have to have a whole passageway or some type of opening. As we look at this picture I have in here, this has a building paper on it. And it might not be real easy to see, but in some places they've taped the seams and everything, trying to make that air barrier really tight, so that we don't have air leaking through there. They have a little spot that they need to finish here and such, but down here. And I want you to pay attention to this little thing here, because we're going to talk about that a little bit later. See this fireplace coming down?
Yeah.
And it's opened
kind of at the base.
Yeah, it's opened underneath. And so we're going to talk about those a little bit further on. But yeah, so by putting this paper on, what have they tried to do? They've tried to cover the holes rather than going around and seal every little tiny hole, because you have little minute holes between the seams in the plywood and the cracks and the joints. See, we're going to have holes where air can get through just because the framing members aren't perfectly tight to each other. There's air spaces. And so the building paper is a good method you wrap it, you seal it up with tape, and you've patched all those little holes behind there without having to individually seal those holes.
Yeah, that sounds tedious.
Yeah, it would be very tedious. Yeah. So to have airflow again through there, we have to have a hole. And then the second thing, we have to have a force to push the air or pull the air through that hole. So if we have no breeze If we have nothing else that creates a pressure difference, then really we don't have airflow, because you have to have a pressure difference before you have airflow. But we'll find that it's really easy to create a pressure difference, and we'll see that as we move on a little bit further here. So can a building be too tight? Maybe, if we don't do what's right. What we can do by making a building tight is we minimize uncontrolled airflow, or infiltration is what we call that. Infiltration, the infiltration of outside air into our space. And provide proper controlled airflow or ventilation. So we're going to talk quite a bit more about these two terms. Infiltration is the uncontrolled movement of air through the envelope. Ventilation is the controlled movement of air into the building.
So we don't want infiltration and we want ventilation.
That's exactly right. Yeah, that's exactly right. And why is that? Because we can control it.
Yes.
Now, what happens with infiltration? You know, we talked this morning about the windstorms we had a couple weeks ago. When you have a building that leaks a little bit, when you double and triple, quadruple, or even increase the wind 10 times what normal wind is, guess what? You increase the infiltration by the same factors. So the wind will just blow right through houses. And fortunately, it wasn't really cold, but I imagine some people, their houses got hot because during the warm days, so much warm air was coming in that the air conditioner probably struggled keeping up.
Oh, that's true.
So wind is a big factor. You know, we're not going to talk about blower door testing today, but you know, we blower door test buildings to see if they're airtight. What we're doing is simulating we had wind on all sides of the building. So infiltration, well, let's talk about this for a couple of these slides. Uncontrolled leakage of outside air into the occupied space through openings in the building envelope. So we'll just call them holes in the building envelope. And this kind of shows a few of them. You know, we have electrical outlets. I mean, I don't know if you've ever experienced it in the wintertime when the wind's blowing, you can go over to plug something in and you actually feel cold air coming through your electrical outlet.
Yeah. I've definitely felt a draft from windows because we have old houses on the East Coast and windows get very drafty.
Yes. Yeah. And they like to preserve the old windows because they're historic and stuff like that. And and they do get drafty. And in fact, some of the drafts you get off old windows isn't even air leaking through them. And we'll talk about that a little bit further, because if you have a big window that gets really cold, it's really cold outside and it's just single glass, what's going to happen to the air that's touching the window on the inside? It's going to get cold, so what's it going to do? It's going to fall.
Yeah.
And so that convective flow that we talked about in the insulation, we get the same type of convective flow against a poor window because the cold air drops. And as it drops, it's going to pull air from above down through it, and you actually get this flow like this against the window. And if you're sitting there, what are you going to feel? You're going to feel very uncomfortable because you got a cold draft.
Yeah.
And the window could be perfectly caulked and sealed, and you're still going to have that drafty feeling. And it's because we got air movement created by temperature difference, not air leaking through the envelope. But both of them are uncomfortable.
Yeah.
And so we've talked about infiltration, and now ventilation that we just mentioned is we do introduce some air into the occupied space by a mechanical means. So that means we have some type of fan that brings some outside air in, or we can do it with exhaust fans, or we can do it with heat recovery ventilators. There's a number of methods. This one is what we call a supply-only ventilation system, where we bring in some outside air through a fan. You know, we filter it, we screen it so the bugs and rodents don't get in it, and then we can discharge a little bit of fresh air into the rest of the building. This can actually be done by hooking into your HVAC system. So when that runs, we pull a little bit of outside air. When we have a supply-only system like that, how do we exhaust air out of the building? What happens is we pressurize the building by bringing outside air, and so however much we pull in leaks to outside, through what? All the holes we talked about. So this is just one of the ways that we can ventilate. We're not going to spend a lot of time on different types of ventilation systems, but there's 4 or 5 options with kind of some hybrid or mixes of both of those or all of those together. That'll be probably another topic that we'll discuss sometime. But let's just remember that ventilation means we're controlling how much outside air we bring in.
Okay.
So,
So are you saying infiltration is bad and ventilation is good?
right.
Isn't energy consumed to offset infiltration air the same as for ventilation air?
Great question. And I've had this discussion, and actually I've had some arguments with some people over it. Why am I making a house tight if I have to bring in some outside air? Why don't I just let it leak so that we get fresh air into it that way? And the question is really, we can control how much ventilation air. We can't control the infiltration. And the infiltration will change depending on the wind. It'll change depending on the temperature outside, the temperature inside. It changes. There's just a lot of factors that will impact that. And with that, if we are not controlling how we get air into the house, then we're not controlling where moisture is moving into our thermal envelope. So if we don't have control over it, we might have moisture either from inside our house moving into our wall cavities, or in humid climates from outside moving into our wall cavities. And we don't want that to happen.
No, I'm very against the mold situation.
Yeah, the mold and the mildew.
Yeah,
and,
not good for the lungs.
And it's not good for the structure.
Right.
So it's important that we control the ventilation, and we do it properly according to what? Building science. Mm-hmm. We've learned a lot. Science isn't something that we always knew, the building science. It's something that we learn over time, and sometimes by mistakes.
Yeah.
So here's a little bit more detailed view of airflow through our thermal envelope, and we look at all these different places. I have 19 different places identified here where air can leak through the thermal envelope. And so let's talk about the airflow through the envelope, and of course let's talk first about the controlled airflow, or the ventilation. Mm-hmm. We can do it with fans, a ventilation system. I should stop at the fans. Just putting a fan in a bathroom actually provides some ventilation, because what does it do? It exhausts some air out of the bathroom, and then how's that air replaced? Through one of these other sources of leakage. Now, we don't build houses that are as good as that cooler. There are going to be some leaks unless we go really, really overboard. And if we go really overboard, and I shouldn't say overboard, if we do everything we can to seal it tight, then we might have the situation where when the fan turns on, we have to have a mechanical means of replacing the air if we build it super tight. But that has to be real tight before we get to that point. So typically you turn on a fan and we're going to leak air in through other places. We can do it with positive, negative, or balanced pressures. So we can remove air from the house, which takes the house negative, and air leaks in to replace what we sucked out of the building, right? Mm-hmm. We can positive pressure, like that first picture where we had a fan. Here we could have an outside air duct tied in with the return of this system, and when the furnace runs, it pulls in some outside air and it positive pressures the house, and then it leaks to outside. Or we can have a balanced system where we have a fan that exhausts and a fan that supplies at the same time at the same rate. And then we have neutral pressures, and we're not pushing moisture into walls or sucking moisture from outside into our walls. We're trying to minimize or eliminate that moisture into our wall cavities. Balance provides superior protection by far. And then we have our uncontrolled airflow. And we're kind of repeating some of these things a little bit. Those are things that are not part of the building design. We don't design a building and say, I want to have 4 square feet of holes in the space so that we make sure we leak plenty. We don't plan on uncontrolled holes in the building. And that's what they are. They're leaks or holes in the buildings, or they're leaks in the HVAC ducts. If we created our thermal envelope here and we had duct systems leaking, it's leaking outside the thermal envelope, so it could either exhaust air out of the space or it could suck in outside air or unconditioned air into the space. And so we can positive or negative pressure by leaky duct systems. And then winds and other pressures that we'll discuss a little bit.
Are some of these leakage spots more cause for concern than others? What would be the main focus?
There are some that really are a concern. And the first one I want to point out is, I don't know if you can read the numbers, but number 15. Number 15 is the wall between the garage and the living space. Now, I don't know if you've heard this on the news, but I pay attention to these types of things. With one of the hurricanes we had a month or two ago, they were, and I can't remember which one it was, but they said they had about 80 deaths. And they said about half of the deaths were by improper operation of generators. They had no power, and so people were running generators. And people lots of times will put a generator in a garage
so I don't have to hear it.
so that, so it doesn't get stolen or whatever.
Yeah.
And of course, you don't want it in the house because it'll kill you if it's in the house. Well, it actually, if it's in the garage and we have a leaky wall between the garage and the house, we can actually get the carbon monoxide off the generator into the house. And we had people died because they were running the generators in their garages. Same thing happens with people in the wintertime think they want to get out the charcoal grill, and they do it in the garage, and they might even open the door a little bit. But you build up the carbon monoxide levels, and if our house is negative pressure for whatever reason, whether it's a fan's running or stack action, which we'll talk about, and this isn't sealed, what do? We draw those products of combustion, the carbon monoxide, into the house. And families have died from charcoal grills in garages and generators in garages. So that's a big one that's important. Another one's important is your fireplaces. Big hole right through our house. And in fact, I've been on thousands and thousands of roofs, through my career. And if you walk over to one of these masonry style chimneys and you lean over the fireplace, you can feel the air drafting out of it. And people don't realize it. There's a damper in there, but it doesn't close tight, or they don't close it when they're not using it. So what happens? Warm air from the house is always drafting up that chimney to outside, which means it's taking the house negative, which means it could draw from someplace else, which means we're exhausting air from inside our house without even a mechanical means. It's just warm air rising. And so that's a big one. And then, of course, we have concerns with gas appliances if those aren't properly vented.
Yeah.
And they can vent into that chimney, or they can vent to another vent that goes up through. So those are three big ones that you really need to worry about. The chimneys, the fireplaces, the vents off the furnaces, and walls between garages and stuff. If we think back to that picture early in our discussion with the house all wrapped with building paper, and it had a garage on it too, we typically don't see them coming in here and wrapping that over the garage wall. In fact, I almost never see that take place.
Yeah, I don't think I've seen it either.
And that's really one of those places that it's more important than out here, because the garage isn't even conditioned in most cases.
Right.
So let's define, I talked about air barriers or building papers. And let's just define that. It's a material that we join together in a continuous manner, and we can see it on this graphic here. They nail and staple it, they cover everything, and then we tape the seams, we seal around the penetrations. You got to hose bib coming out, you have an electrical box coming out, you have the floodlight. You make sure you seal all those things, tape them, and that's how we seal that thermal envelope.
Does the air barrier stop rainwater?
That's another good question, because what we see this on there sometimes, and in fact, we call it house wrap, and it does stop the rainwater. The rainwater that might get through will run down it.
Okay.
But it is not a vapor barrier.
Okay.
So plastic sheeting is not something that we'd want to put on there. Because people say, well, isn't plastic sheeting a really good air barrier? Won't it stop any air from coming through? Sure, it'll stop the air from coming through. But what does plastic also do? It stops vapor from being able to move through it.
Right.
So these papers stop the rainwater. They'll shed it, and it will just kind of run down it. Uh-huh. It's kind of like a rain jacket.
Yeah. That's
Not a
what I was
rubberized one, but
Yeah.
Like a windbreaker type rain jacket.
Or like Gore-Tex maybe.
Yeah, Gore-Tex and stuff. It sheds it, but if you sweat, it breathes enough that you can, the moisture can dry away from your body.
Right.
And so that's the type of materials we want. Because if we put a vapor barrier on the outside in our climate zone where it's cold, and if we get any moisture coming from inside out and it strikes that vapor barrier, it's going to see cold plastic, and what's going to happen? It's going to condense.
Yeah.
And so you'd have moisture on the backside, and moisture will destroy your building.
Yeah.
And we get to the mold thing and everything else again. So our air barriers need to have a perm rating to where any moisture that might be on the inside of it has the ability to move through. And so we have the ability to do some drying. So airflow through the thermal envelope. It's interesting nowadays. Back 40-something years ago, when I first started doing HVAC, we built pretty simple houses. They were little squares or rectangular shape. And what do we see now? You go by townhouse projects or apartments or new houses, and what do they have? They have a base sticking out here and a cantilever here, and they have lots of angles and everything. They're not plain straight. And we have lots of this type of stuff that occurs, kind of like that first picture we showed where the insulation goes up around that little attic space. Well, every time we make any of these turns and stuff, we have areas that we might need to seal. And so sealing the thermal envelope, if we're not putting that building paper on, or we're not comfortable that it's going to seal it properly, we have lots of other places we need to seal. And it's not really expensive on some of these, because before we put that wall on, we can put something down for a sealer. When we put this block in, we can seal the block when we put it in. So some of the things, it's just a process change. A framer that understands these principles can do a great job in eliminating air leakage by just changing his habits or his practices just a little bit. So many little holes equal a large single hole. I don't know if you've ever seen him, but we've had him come into Utah a number of times, Mark LaLiberte and some of the other gentlemen from Construction Instruction.
Yeah.
And they come in and they talk, they do really great talks on building science and how we can build a home that's a tight home. And I love what Mark does in every class just about. He takes a big piece of paper off the easel where he's writing things, and he'll fold it in half, and he'll say, do you want a hole this big in your house? And no one wants a hole that big in your house, leaking air through it. And then he talks about how all those little holes in your house add up to a hole this big. And we can verify that through blower door testing. And then if we do the proper air sealing, the better we seal, the tighter we go. He folds the paper up and says, well, maybe you only want a hole this big. And theoretically, we don't want a hole at all.
We don't want any holes.
We don't want any holes. Now, to not have any holes is going to literally take cooler type construction.
Yeah.
That's
And it's
really
going to be expensive.
That's going to be expensive, and it's going to be hard to do. But there's some technologies out there. Insulated concrete forms, ICFs, the big foam blocks that look like Legos. You stack them all up, then you pour them full of concrete. They don't leak air at all. Foam and concrete this thick isn't going to leak any air.
Yeah.
The only place you're going to leak is around your windows and doors and your ceiling.
Yeah.
And so they make really tight houses that you have to ventilate. So that's a great question. How large a hole do we really want in our house? How large a hole do we want to have that we have to pay extra money to heat and cool our house because we basically have an open window all the time? Now, some holes may be required for combustion air and chimneys and vents and stuff, but actually we can get around those if we want to do the right things. And we'll talk a little bit more about that. Pressure differences. Remember we said if we have a hole and then we have a pressure difference, then we're going to get air moving through that hole in our thermal envelope. So pressure differences, the first one, and we already talked about, is wind. Then I talked a little bit about stack effect, heat rising. Now, many people have had this experience where you have a wood-burning fireplace, and when you try to light a fire, it smokes into your...
Yeah.
Right?
I've seen it, yeah.
Yeah. And so what do? You take a newspaper, crumple it up, and you light it on fire, and you shove it up as far as you can into your chimney. And what are we trying to do? We're trying to warm the chimney a little bit so it does what? So it'll draft.
Suck up the air.
So we get that stack effect. So we get heat rising. So stack effect is creating when we have warmer air relative to the other air around it. Warm air rises, cool air falls. And it's just a natural phenomenon. It's a building science principle. Warm air rises. Air expands, it's a little more buoyant. How does a hot air balloon work? Warm air rising.
Right.
We make it really warm, and we can lift the big balloon off just because of warm air rising. So that's stack effect. Then, of course, fans, and then HVAC design flaws can create pressure differences. Now, one of the most common ones, a couple of the most common ones, are duct leakage. But a real big one is lack of return air paths. Now, if you think about this and other people think about this that might be watching this, let's say we have a little 2-bedroom or 3-bedroom house, and we put a supply air in every bedroom because we want heat or cool air, but we put all of our return air out in the hall. Or if we have an apartment, we have a single return air in the ceiling or someplace, and then we have supplies in the rooms around it. Well, if the doors are closed and the doors fit fairly tight to the carpet, we have a challenge with the air getting back from that supply air where we discharge it into the room back to the return. Because that HVAC system is doing what? It's just circulating air inside. We bring it in through the return, heat it or cool it, send it out to the various rooms. Well, if we have a room that kind of isolates or is sealed off and blocks the path back to the return, we create a positive pressure in that bedroom. We create a negative pressure out in the living space where the return is because it can't get all the return.
Right.
So it gets less air than it sent out, and we can't get all the air from the bedroom back to it. So we positive pressure the bedrooms, we negative pressure the living space, and what's the return path? We leak air out of the bedrooms to outside. We leak air into the house through in the living space. And so our return path in some of those situations is outside. We're creating pressure differences simply because our HVAC system did not account for a return path for all of our supplies back to the return.
Does that happen frequently?
All the time.
Oh, wow. I'm surprised.
All the time, in fact. In fact, a number of years ago, probably 10 years ago, a few years after I started doing inspections, after I got out of the HVAC business, the code has said for a long time, design your duct systems per ACCA Manual D. And Manual D stresses a return path. And so I started teaching this, and now in Utah and in other parts of the country are doing the same thing. We're seeing more and more that we're identifying a return path.
Oh, good.
Whether they put a return in the room or they put a grill or some type that allows the air back to the return. Simple thing is put a return in bedrooms, but it costs a little bit more money.
Yeah.
So yeah, it happens all the time.
Wow.
And it's happened millions and millions of times. But what are we looking at? Building science has recognized this. The system's worked. That people say, my old home, I could close the door and it worked fine. Yeah, because it would leak outside and then we'd bring more air in but we were paying for it.
Yeah.
And so, yeah, it's just building science. So, just want to reiterate this one. If we leak some air out, if we exhaust some air out of the building, we're going to have air come in and replace it. If we have air come in from outside, whether it's through the wind or a positive pressure fan that sucks air from outside and dumps it into the space, we're going to have to leak a certain amount out. We don't create air inside the space. It's always going to strive for a balance. Air in equals air out. And it applies to both controlled and uncontrolled, whether it's infiltration or ventilation. If you bring a certain amount in, it has to leak out. Now, when we get into big buildings, large commercial buildings, they're bringing in so much outside air to maintain air quality in the whole building, like a building we're in right now. Mm. And so they are pulling it in with their HVAC system, and then they have big power exhaust fans that remove it, because we can't rely on it leaking out of the building because we have so much interior space that doesn't see an outside wall.
Yeah.
So it'd be stale and stagnant in the middle part of the building. And so we have to mechanically make sure we have that controlled ventilation done according to engineering principles. Okay, the next one, let's talk a little bit about building too tight and vapor barriers. Now, I remember it real well because you have events that happen in your life, whether it's work or someplace else, that something crazy happens, and so you remember that event happening. And so back in the 70s, 76, 77, when we were talking about the energy crisis, one of the things that came out of there was we need to build a tighter building. And so someone came up with the brilliant idea, and we normally put VisQueen vapor barrier on the warm inside surface of a wall here in Utah. Mm-hmm. So we can put a vapor barrier on. If this was an outside wall, we'd put a vapor barrier behind the sheetrock so that we don't get the vapor into the wall cavity, the moisture into the wall cavity. And if done correctly, they work well. Well, someone came up with a brilliant idea. Well, if it stops air leakage so well there, let's put it on the ceiling. And so therefore, a matter of a few weeks in Utah, the code was put a vapor barrier on the wall, put a vapor barrier on the ceiling. Now, and I saw it and I thought, well, that doesn't seem like it's going to work very well because we have moisture and stuff that rises up into attics, that goes through the light boxes and stuff. And I was working on a commercial building that was just 2 levels, one half in the ground and then the other one up out of the ground. And it was over on 5th East and 45th South. And so they put this VisQueen plastic on the walls and on the ceilings. And I was in there working on the HVAC, and the drywallers came in after insulation and VisQueen, and they put the drywall on the ceilings, they put the drywall on the walls, and then how do they heat it in the middle of the winter? They bring in those big salamanders, we call them, big propane heaters, and they just let them run wild. And yeah, they dump carbon monoxide and everything in, but you let them run during the night so that the sheetrock metal dry. So they put all this wet drywall mud on all the joints, first coat with lots of mud, lots of water, and then they put these salamander heaters in there. Now, one of the byproducts of combustion is water. When you burn a hydrocarbon, you get carbon monoxide, carbon dioxide, and H2O. It's the steam you see coming out of furnace vents and all those types of things. So they put these heaters inside that created moisture inside. They put all that drywall mud on that created moisture inside. And then they warmed the space up with the heater, so where did all the moisture go? It went up with the warm air rising, and it saturated the ceilings. And the next morning when we all got there to work, the ceilings were sitting on the floor. Literally, the ceilings had all caved in because what happened? It was just like you'd saturated with a hose that got saturated.
Got too heavy.
It got heavy. The nails and screws aren't going to hold up anymore because it's wet paper and gypsum.
Yeah.
And so the whole thing fell in. And so that was short-lived. No more vapor barriers on the ceilings. And so those were some of the hard lessons they learned. It was decrease the energy cost and decrease air leakage, but drastically increase moisture problems, indoor pollution levels. We have health risks, we have mold, we have rot, and we have occupant complaints. So it did not work. And the big problem was, if we look at the bottom, they relied on natural ventilation, which did not work, which doesn't work today either. Now the question is, what's natural ventilation?
Yeah.
Natural ventilation is we crack the windows, we crack a door. It's not going to work very well. Number one, people don't want to open their windows in the summer. They don't want to open their windows in the winter.
Especially with the fires going on.
Yeah, with the smoke and everything that we bring from outside. And our code still allows us to do natural ventilation. Now, that's a whole nother subject that we'll discuss in another class or in another podcast or something. But we're still doing it today in some cases. And it really needs to disappear out of the code because natural ventilation does not fit with the other things we're doing to the building envelope. We really need to have mechanical ventilation.
Yeah, it seems quite counterintuitive.
Well, I'm not pointing fingers, but what we have amendments to our state code, to our energy code. If we did not have amendments to our state energy code, the way the code is written, every residential home or apartment up to 3 stories in high would be blower door tested. And every one of those blower doors tests would have to reach a level of 3 air changes at 50 pascals or lower. So we have to blower door test everything, and this is amended out so you don't have to do it, you can do it. But if we followed the code exactly, we'd test everything to a level of 3 or lower, but then there's a trigger in the code that says if you're tighter than 5, so if you're lower than 5, you have to mechanically ventilate. You cannot use natural ventilation. So without amendments, our code would require every new single-family dwelling to be mechanically ventilated. But with the amendments, they have an option that they don't have to blower door test if they want to follow a checklist. And so we really kind of have a conflict in our code that may be saving a little bit of money, but it's creating potential problems
in the long run.
In the long run.
Yeah.
Expensive problems.
Yeah.
So, my word of caution to builders, and a lot of builders have come to the classes that we've done, and they understand this, and a lot of them have done the right things. They're putting in an exhaust fan that runs all the time so that we're at least having some continuous ventilation. We maintain some fresh air. And if we're doing things like in our bathrooms where we have moisture, humidity sensors on our fans, when our moisture level comes up a little bit, we get rid of it. You know what I mean? We just get rid of it. And so those are some of the things we need to do. So these are some hard lessons, and unfortunately, maybe we haven't all learned them. And so a balancing of energy efficiency with indoor air quality is what we want to strive for. So we want to build a tight building. And I'm going to repeat, I don't think you can build a building too tight if you do the right things, with well-designed ventilation system so we can provide acceptable indoor air quality and reduce occupant complaints and reduce moisture levels and all those things. So we can build a tight building, drastically decrease energy use, provide a well-designed ventilation system, properly installed, balanced, and operated, and the result is a much healthier building than a leaky building. You know, going back to that question, why don't we just have a leaky building? Well, we're still not going to ventilate the whole entire building. We might just ventilate around the perimeter of the building, but we're not going to get fresh air out of the center of the building or to the center of the building. So improper airflow, what are the effects on occupants? And we've talked about some of these already. Pollutants, mold growth, we might have radon, smoke, CO2, VOCs, cleaning chemicals. Moisture and mold, because of poor humidity control, condensation. You know, it's really a simple thing when we talk about condensation. Why do we get dew on the lawn in the summertime? Because we just hit the right temperature that we drop the moisture out. Now this isn't warm, this isn't cold anymore, but when I got this out of the fridge, we'd get what on it? A little bit of moisture.
Yeah. You
coming from the East Coast, you know that if you set a drink with ice in it on the
sweats,
it pours water.
Yeah.
So depending on the humidity and the temperature, we get condensation. And it's what we call dew point. Mm-hmm. And it varies depending on how much moisture and what the temperature is. And we could get condensation at different times of the year, even in the summertime in our air conditioning ducts and things like that. So those provide some effects on the occupant. You know, mold growth isn't something that anybody wants to see. And then we have some combustion effects that come about from backdrafting gas appliances, from the generators, from the charcoal grills and the gas grills and the propane grills and whatever. I'm by far not saying that we don't want to use that gas appliance, because I love to cook on gas and I heat my water with a tankless water heater by gas, but we do need to be aware that when we burn something, we have the potential to create lethal carbon monoxide. With that, conditioned air is wasted out to outside, and we can solve that with a direct vent appliance.
Is the direct vent appliance safer than others?
Yeah, it is. It's
And can you elaborate on how it solves the combustion issues?
Sure. Yeah, and I threw in this slide because I get this question a lot. So this is a direct vent furnace. And if we look at it, I can find my cursor now. Well, I can point. I'm close enough. If we look at this furnace, here's our blower compartment. So when this is installed, we bring return in the side or the bottom, and we have our supply going out. We have this heat exchanger in here. And you will notice that the burners, it says burner sight glass, so the burners are inside this little box. And then we have a fan that actually pulls the product's combustion. The flame is pulled into this heat exchanger. The airflow across it pulls the heat off, uses it to heat the space, and then this fan exhausts outside. So this is what we call a direct vent appliance. It brings combustion air directly from outside in a pipe that's sealed into the burner compartment, goes through the furnace, and then back outside. Nowhere does the flame in this furnace see the indoor environment. Now, a non-direct vent furnace will use an open combustion. So you won't have a burner enclosed in a little sealed box. Mm-hmm. You typically down in here, you have burners, and you can actually see them. You pull the door off, and you can literally see the flame right there.
Oh, wow.
And it's drawing air from inside the space. It rolls up through the furnace, and then it exhausts out a metal pipe that goes up through a chimney or a vent. And so it relies on the heat in the product's combustion to carry it out, just like a fireplace. Mm-hmm. So that is a non-direct vent appliance. Water heaters are the same way. I don't know if you paid attention to a water heater, but they have a little cone on top of them with a vent pipe coming off of it. Well, that cone draws air from inside your space. The burner draws air from inside your space. So if something were to go wrong, or if the building were to go really heavily negative pressure because someone messed something up, you can actually draw products of combustion into your space. Yeah. And when that happens, people get sick and people die. And we hear about carbon monoxide deaths every so often.
Yeah.
And lots of times they're tied with vent systems. So a direct vent appliance
is the way to go.
It eliminates drawing air out of the space for the combustion process, and it eliminates risk of exhaust fans reversing the vent and drawing the product's combustion. So it solves a lot of issues, and it's really the best way to go. They've been out since the early '80s, and so they're pretty good appliances, and there's no reason not to put one in other than they cost a little bit more. But they do offset some of the things that we have to worry about, the improper effects, of that airflow through the envelope on the occupants. So I just threw this one in so we understand a little bit better. So what does this improper airflow do? And I have those, we've talked about these. So the wind, we see what happens with the wind. We blow against one side of the building and some air is going to leak in, right? Yeah. So what's going to happen? It's going to push air out the other side. Or stack effect, because we're warming this air, it tends to rise between levels.
Yeah.
And so if you take a magnehelic, a low pressure gauge, you can actually measure the pressure difference between the lower level and the upper level. This will be positive pressure and this will be negative pressure. And so it draws air in from the lower levels of the building. Obviously, it's not going to draw too much through the dirt, but it'll draw, right at this level in and here. And then by the time you get up to the upper level, we're all positive pressure, and then we're leaking out. And that's the stack effect. It's the same thing that makes a chimney work. And then we have combustion and ventilation. So we can have fans and dryers, range hoods, and all those things that suck air or exhaust air out of our space. A gas appliance that's burning and sucking air out of space because it needs air to burn, right? Mm-hmm. It needs oxygen to burn. And then that goes up. So on this one, back in the 80s, and I keep going back because I experienced all these things. Back in the 80s, the gas company came around and the building inspectors said, do you know what? We're burning air out of the space. We call it combustion air that's used for that heat production in the furnace. And we're making our buildings a little bit tighter. And because we made our buildings tighter, we're worried that they're not going to leak enough. And so we have to add combustion air duct. And so going back to the 80s, we build this tight envelope. And then the code says, yeah, but you got to provide a duct that comes in to provide combustion air. So we build it tight, and then we cut a hole in the wall to let air in it. And it really doesn't make a lot of sense.
Yeah.
Some jurisdictions, some inspectors said, no, if you're going to do that, you have to isolate it in a room. But it really didn't say that in the code. So back in about 2013, 2014, a number of us in Utah, with some friends from across the country, we wrote a code change that says if you have that open combustion appliance, the burner sees the indoor environment, with that combustion air coming in, you have to build a little room that's a separate environment that seals it from the rest of the house. So we get the benefit of the air sealing, and we reduce the risk of having the combustion appliance open in the house.
Right.
So we just, we basically require it to be in its own little isolated room. And
makes sense.
When we did it, one of our goals was the code requirement now says you don't have to do it if it's direct vent. because you don't need to, because the direct vent brings its own combustion air. So, again, all these things affect the occupants. So they have cold drafts in the winter, hot air in the summertime, convective flows. You know, I have a 2-story house, so I have 3 levels. My basement's almost always cold, whether it's winter or summer.
Yeah.
Because the cold air falls. So when my air conditioner runs, you know, the cold air drops down there, and upstairs where the heat rises is warmer. Now, sure, you can fix and minimize that with proper HVAC design, but you're still going to have that occurring. Cold air drops. So cooler down here all the time, warmer up there all the time. If you do a load calculation, which is a topic for another discussion, and properly size the furnace and air conditioner, they're going to run longer cycles. You're going to get more even circulation and distribution. And then we have less of that problem because we're adding it at small amounts and keeping that air circulating. Oversizing, you remember when you talked right at the first about just throwing a furnace and throwing an air conditioner? If it's oversized, it turns on, runs for 5 minutes, and shuts off. And then what happens? All the air stratifies up, and you're cold low and you're hot high. It really doesn't provide a level of comfort.
Oh, here's my mold picture.
Here's your mold picture. Isn't that great?
Yeah.
That's actually kind of gross, isn't it?
It is nasty.
When I went out to investigate this, I got a call from a guy. He says, "Can you come take a look at this and tell me what's happening here?" I got up there, and this is the insulation that lays up against the rim joist. This is the rim joist on the outside of the building, and it's a home. And I pulled this insulation down, and I went, "Ooh, where's my mask?" You know what I mean?
Yeah.
Because see it out here?
It's spread.
It's everywhere. There was so much moisture, but why was there so much over here? Because it's colder there.
Okay.
That's outside on the other side. So that's colder, and that's why we had so much more moisture there. And it just goes right back to the thing we were just talking about. If we have, for some reason, airflows that are moving that moist air that direction, then we greatly increase the amount and the likelihood of mold growth.
Yeah.
So airflow can transport the moisture into ceilings, walls, and other framing cavities. Moist air contacting a cold surface may create condensation. Just depends on the conditions. Obviously, the conditions were right here.
And how did this get fixed? Like how do you solve this problem once you're already there, you know?
Well, this was a crawl space.
Yeah.
Remember we talked about the crawl space, and I said it's not my favorite thing. This was a crawl space that they did not put. Well, they put the vapor barrier, the heavy plastic on the dirt, but they didn't seal it up against the foundation.
Okay.
And so I went out there. I was hired to investigate it, and the plastic was just like a blanket laying on the ground. You could pull it back, and guess what? It was just soaking wet.
Yeah.
And the guy says, "How could you get so much water there?" And my comment was, you remember Boy Scouts? They tell you if you're lost in the desert, if you take you dig a hole, you lay a piece of plastic over it and put a rock in the center so it kind of goes down like a cone, that moisture will come up from the ground and collect because we have moisture in the ground.
Right.
It might be deep. Well, this was in a location that was actually up Provo Canyon, so it wasn't real far from the Provo River. And there's lots of moisture in the ground. And so what he had to do was he had to come in and put a whole new vapor barrier. They ran it up the wall, glued and sealed it to the wall, insulated the wall real good. They had to bring a guy in, and they used dry ice to
kill it.
To blast. They sandblast with dry ice particles because after it's blasted, it just disappears because it's just carbon dioxide.
Right.
And so they blasted it all. And then I told him, I said, what you need to do is spray foam on the rim joists. Because even if you have it all cleaned up and you put a piece of fiberglass back up and we get a little bit of moisture in there, what's the moisture going to do? It's going to migrate through the fiberglass insulation, because the fiberglass insulation doesn't stop moisture.
Right.
So one of the things on the checklist in the code says you have to have an air barrier on your insulation in the rim joists. And a lot of people don't do it. And this is the problem that happens. So spray closed gel foam, a couple inches of that. What does it do? You put that spray foam on, and outside surface here, inside surface here, the moisture hits the inside surface, but it's warm. Because why? Because we have all this insulation that's stopping the heat flow to outside. This surface is cold. With the insulation up there, we still have air movement through it because we don't have an air barrier. It's not enclosed on all 6 sides, and so the moisture still gets through, and we're going to have the mold. So hopefully he sprayed foam. I didn't see it after, but that's the direction I gave him.
Or he'll be doing it again.
Yeah, he'll be doing it again, because it's almost impossible to have that perfect seal on that vapor barrier on the ground, or someone crawls across it and pokes a hole in it, and then the moisture's coming through. So it's building science, and it's something that we've learned through mistakes.
It's surprising too, because Utah's so dry, to see like a mold issue in a Utah home. But like you said,
that is such a great point. I go to code hearings where the codes are developed and everything. I've been on some ACCA committees where we talk about load calculations and duct designs and everything. And everybody keeps telling me, you don't have moisture issues. And no, we don't have moisture issues like those people do. But we get cold. And because we get cold, we have moisture issues that are different, but even every bit as critical or even more critical than some of the other moisture issues, because it is so, when it's cold, we got condensation. I teach every year in Houston, Texas. And I don't know if you've ever been to Houston.
It's humid.
It is so humid in Texas, in Houston, much more than any place else, because they're not that far from the Gulf.
Right.
And we joke about it. And I have to teach completely different in Houston because they have a different
climate.
But moisture is still moisture, and it condenses in their air conditioning ducts, and they have to remove the moisture, with the air conditioning. We don't have to do those things, but this is what we have to deal with. And there's thousands and tens of thousands of houses in our cold climate that are having issues in walls, and they don't know it. But that's what's happening.
Yeah.
So this was in the crawl space, not in a basement, but I've seen it in basements too, and it's not a good thing. Wood rots when it absorbs 30% of its weight in water. And this, I don't know if you're familiar with this, but this is OSB, and most people are familiar with this that are going to be watching this. This isn't normal plywood. Plywood has layers, and they change directions perpendicular to each other in layers. OSB is just wood chips. They just chunk it up and they compress it with glues. And it's really strong and it's good material, but it's not good when it gets wet.
Okay.
It falls apart and it delaminates and it swells, and so it doesn't behave well in water. In fact, it's once you get it saturated and it stays wet, it's gone. It has to be replaced. There's no fixing or repairing it. So our solutions, they depend on the climate, like we just talked about. Proper air sealing stops the airflow. This insulation, and this looks like it's bigger than it really is. This is just a piece of insulation. If you stood it up, it's this depth, so it's just against there. But it isn't air sealed. It's got that side, this side, nothing on the bottom, and nothing on the face. And so it only has 4 of the 6 sides sealed. And so what's going to happen, air is going to come up through or drop down through, because it's against that cold surface. It'll drop down through down in the crawl space, and it's just going to circulate around, and we're going to get the moisture due to the convective flow through the insulation. And the insulation is almost useless at that point. And we even have colder temperature because the insulation's wet.
Right.
Mechanical ventilation, that's one of the things we have to do, and we have to do it correctly. Insulate to minimize cold surfaces, and then I put CI. CI stands for continuous insulation. This could have been solved if they had put continuous foam board on the outside of the building. Now it's a little more expensive, but you might have seen buildings that they put pink or blue foam or white foam on the whole exterior and then put the stucco over it. That gives you some continuous insulation. And if it was on the outside, on the other side of that board, what does it do? It keeps this surface warmer, and then it doesn't condense.
Right.
Because we're insulated it. So it's similar to spraying the foam, but even better because it's on the outside and it's continuous insulation. I think this is a great slide. I really do. This is one of my favorites because it really tells the story. We can have fleece or a sweater or a sweatshirt or something, and it keeps us warm until what? Until we have a little breeze. And then what are we? We're cold.
Yeah.
And all we have to do is just throw a windbreaker. We just throw an air barrier on, and how much warmer are we?
Yeah.
It's
a lot warmer.
A lot warmer.
Solves a lot of problems.
It solves a lot of problems. It's the exact same thing with our insulation. If we don't have the air barrier, the air just moves through the insulation. You know, a down jacket, if it doesn't have Gore-Tex or something on it, it's not going to do anything.
No. Yeah.
And so the insulation traps pockets of air, and those stagnant air pockets create an R value. But as soon as we have air moving through it, we lose the R value, and it doesn't work anymore as an insulation. So if we stop that movement of scrubbing away those air pockets, it works. You know, so that's why we say all the time, put on your layers, we create those air spaces, and then put on your last layer, something that will break the wind. Then you can take off a layer and put your windbreaker back on. Take a layer and put your windbreaker on. Not only keeps you dry and sheds the water, but it also stops the wind moving through. You keep warm, but it breathes enough to keep you. It's not like the throwaway rain jacket you put on and instantly you're sweating.
Yeah, the ponchos.
The ponchos and stuff like that, or the gloves that you put on, and when you take them off, the latex or sealed gloves, your hand is just soaking wet.
Yeah.
Duct leakage. If ducts are outside the envelope, we exhaust heated or cooled air. So if we have a duct system in an attic, and then we have air leaking through, if this was in an attic, it's not, but if these were in an attic and the system's running, we have air that we just spent money to heat or cool, and it's blowing out into the attic. So what's that going to do to our interior space? It's going to take it negative because we just exhausted some air with fan horsepower from our furnace. So we're throwing air away, has to be replaced with air leaking in. So we create a negative condition. If this was a return duct, so it's drawing air back to the furnace, then it would be drawing 140 degree air, whatever the air is in the summertime, back into our return system, and it's not going to work. You know, I mean, it's going to add all this heat to our system that we have to spend money to remove in our summertime condition. In either case, whether it's a supply duct or a return duct leaking, we create a pressure imbalance, and it increases airflow through the thermal envelope. So duct leakage increases the airflow through the thermal envelope, and it reduces airflow to the design location. This system supposedly had a design to it, and they wanted a certain amount of air delivered to a room. Well, it's like a leaky garden hose. If you leak part of it before you get out to your sprinkler, you're not going to get it where you want it.
Right.
You're going to get it someplace else. And so we would like to have it where we want it. And when we create those pressure differentials, then again, we're moving air through the insulation, reducing the effective R value.
If the duct is inside the thermal envelope, why would it matter if it leaks a little? Like, how was that? What's the impact of that? And
Okay, and this is a question I've received so many times, and I was actually a little bit guilty of it 25, 30 years ago when the code started saying we need to start sealing our ducts. And I'd say, if this is in a basement, now I didn't allow work like this when I had my HVAC company. But if it's in a basement, it doesn't leak to outside. It's just leaking in our basement. It's still inside. Well, sure, it's inside, but it's not where we want it.
right.
It's not in the room we want it. If it leaks like in your basement and you want the air upstairs and you have a lot of leaks downstairs, then what happens? Your basement becomes positive pressure because you're blowing all this air in the basement and the returns are upstairs. And so what do we do again? We create that pressure imbalance. And so we're going to end with more leakage in and outside, in and out of our building.
Right.
So anytime we do anything that creates a pressure differential, we increase the amount of infiltration. Remember, infiltration,
We don't want it.
we don't want it. It's impacted by the size of the hole, and it's impacted by the pressure differential. And when we create pressure differentials because we do a crappy job, then we increase the amount of air that's leaking in and out of our envelope. And it's not possibly where we want it, and we might be putting moisture into a wall cavity, or we might put moisture into a ceiling cavity. And all we do is add to the problems. We're creating those conditions that occurred back years ago when we didn't have the science which we have now. Now this one, I took this picture just a month or two ago.
Wow. What is it? What am I looking at?
So here's a piece of duct coming across. These are two pieces of duct, and this is the connection. And they didn't get it to fit quite right. There's a little cleat that slides up. It's kind of a U-shaped cleat that slides up between these two little bands on the ductwork. And this is a big leaking hole in the ductwork. And that's a pretty substantial leak.
So how would you patch that?
Well, number one, they should have done a little bit better job on the ductwork. But you see this gray stuff that they've smeared all over?
Yeah.
In both of these cases, they have big holes. They didn't push these little tabs down tight. So that's a hole into the duct. On all the way around, each one of those is leaking. They smeared the stuff, but it didn't seal the hole, did it?
No.
It didn't seal it at all. This is in a basement, and so they smeared it up the side where the inspector would see it, and you can see where it's all smeared there, but they didn't even put any on top where this big gaping hole is.
Yeah.
So, I mean, they could seal it, they could caulk it, and then smear this stuff on it, but it's poor craftsmanship on the ductwork itself. That you should be sealing tiny holes with the duct sealer, not massive holes with the duct sealer. So, duct leakage adds to the same thing, same problems. So this next one, these are some great pictures, and I took these at the same time I took the other one, but this was in a different house. And these are some pictures of ducts in a garage. So this is that bonus room that we talked about right at the first. So this is in a garage. These ducts come up from the basement. This is the main floor. There's second floor up above, all these ducts, and they're boxed around them all, and then they're going to insulate them. Now the ducts require a certain amount of insulation, and they also and these ducts are not insulated, obviously. They're just sheet metal ducts. There's no insulation on them. Now, lots of times I see that someone comes in and they want to just insulate this with batt insulation. So they put a piece of fiberglass batt here and there. So every one of these, between the framing members, they put a piece of batt insulation. So it's just a piece of blanket, that's fitted in there. And then they do the same thing up in the joist, and they pack it in around the ducts and wires there. But what it does, it leaves, so you put a piece of bad insulation here, then you have all this space up above that's just air. And you end up, when you think about it, if we just insulate around maybe they put a piece up the side here, maybe not, but we end up with all these air spaces. Well, what happens if you have air spaces and fiberglass insulation? We get air movement, the air moves through the insulation loses its value. The other thing we have to think about on this is if the ducts leak out there, they're outside, we're blowing the air into the garage. We're not keeping it in the house. Mm-hmm. Now these look like they're sealed pretty good. They've done a pretty good job, and they've sealed, everything pretty well. So prior to insulation, if they bat it, it's not going to work. The insulation is not going to work because we're going to have air flow through our thermal envelope. And our thermal envelope, in this case, literally comes up this wall. This is inside the garage, so the other side of this is inside the house. Then the thermal envelope comes around wherever they insulate. But again, we're not going to end up with bad insulation with a complete air barrier. We're going to have all these air spaces up in there, and it simply doesn't work. And I see hundreds and hundreds of them do it that way. And you can argue about if the code actually says that, and I think it does. In fact, I know it does, but not everybody enforces it. Let's look at the next picture. Now, this is a great system. This is what we call a bib system, blown-in blanket insulation. And they literally come in, and this is a house just like, if I go back, so it looked kind of like this before.
Yeah.
And they come in with this net, this fabric net, and they staple it over all those framing members, and you can see it kind of looks the same, doesn't it?
Yeah.
And then what do? They poke a hole in it, and they take a hose, and they just fill the entire cavity full of fiberglass.
And that stops the airflow.
Stops the airflow. We have an air barrier on all sides of the insulation, because what's the air barrier going to be here? They're going to put drywall on it. Mm-hmm. They'll drywall it. And so we have this insulation with that windbreaker on all sides of it. This is a great system. It works so well. It stops the air movement. They put the drywall on and seal it well. It really does a good job. Now this is a wall, see, it goes to inside the space, inside the house. This is the wall that really probably should have had some Tyvek or something on it. Because that's the wall between inside the house and the garage. Mm-hmm. And so that's...
If you had your generator in there.
If you had your generator in there or your grill. And now it's framed pretty well.
Yeah.
And you can use the OSB for an air barrier if you tape or caulk all the seams. Mm-hmm. And you caulk around these. Now this box they cut in fairly tight, so it's not going to leak very much. And if they drywall it and then seal it, the drywall can be an air barrier too, as long as you seal it, And we'll talk just a little bit more about that a little later. But yeah, this isn't a perfect house, but they've done a lot of things right. And this is one of the big things that really is making a big difference. And I'm sure that one of the reasons they started doing this is because they had complaints of comfort in the bonus room. Mm-hmm. So by doing this, they made sure that they had a good insulation package on the floor system, and they're stopping airflow too. We don't have that airflow moving around within it. Okay, remember we pointed out earlier in that one early slide the cantilever where the fireplace stuck out?
Yes.
So I'm going to define a cantilever right now, because there'll be people that maybe are not completely sure what a cantilever is, and I have other slides that we need to talk about on this.
It's an overhang, right?
It's an overhang, yeah. And so what they do is these are self-supported because, see, this is a joist, and there's a double joist, and there's the joist, and they run all the way in, and so there's a joist sitting here with just a couple of joists with just a little bit overhang, but they go way back in.
Okay.
And so because of the length inside, you're fine. It's not like it's going to
Topple over.
Or anything like that, because it's self-supporting. And there's structural requirements on how much has to be inside for how much you have overhanging.
Yes.
And so little 2-foot overhangs are great. This one's a bay window. That one's a fireplace. But I brought this up because, again, we're looking at the insulation. Now this is the same homes that they're blowing insulation in the garages. So if they were to blow insulation in here, they would net the bottom off, and then they'd blow insulation in.
Okay.
What they've done is they've just shoved some bats in. Now, what's real critical is at least they have to put something on the bottom that air seals it, and oftentimes they don't. Mm-hmm. In fact, my house I'm living in right now, it was built, it was an existing house when we bought it, and we have a bay window like this. And when I first moved in, we moved in August, and in October we had a cold day, and I walked down in my bare feet across the hardwood floor, and it was really cold, and it's because the wind was blowing.
Right up in that
and
cantilever.
It was coming right up through that cantilever, because all it had was some aluminum soffit material, and the air was just going right across inside my house. I mean, it was cold.
Yeah, that's not fun.
No, it wasn't. And so I ended up going out and tearing that soffit material off and putting something on the bottom, and actually put a piece of sheet foam on it and stuff to seal it up. So this really isn't a good detail. What they've done isn't really the best practice here, and they really, technically it's really not code compliant. And we got some other slides that we'll look at that will show how big of a deal this can be. But the cantilever, we need a proper installation of our insulation. We need to make sure our gaps are sealed, and that includes sealing down here. And we need to be concerned there's a duct that comes out, that's above the insulation that blows up in front of a window. We have a rim joist that runs around the outside of this. That's the joist that's vertical, and these other joists come and tie into it. It looks like they've insulated here, but did they insulate around the face of the rim joist? Probably not. And so we're going to have some air gaps in there, and when I look at there, it's concerning to me. And so, of course, what do I want to do? I want to go inside and see what they did inside. Mm-hmm. And so we look inside, what do we see?
A lot of light.
We see a lot of light. And some of these pictures are ones that weren't insulated on the outside yet, but they are going out into the cantilever, and the next one we do have insulation. But it's extremely critical on these cantilevers to address the air barrier and the ceiling, because you can see right here what's happening here because of the cantilever. You see the little notch here? These notches are for the bolts that hold the house, this sill plate down to the foundation.
Right.
And there's a notch there for the bolt, but what's on the outside? The plywood comes down over it. If we back up, that picture doesn't show it very good, but see, the plywood comes down the face here, and when we get over here, the plywood keeps running, and it's covered those holes. But because of this cantilever, those little notches for the bolts, we aren't covering them on the outside.
Right.
They're up inside this thing. So you can see where the cantilever starts right here and then goes over to about here. Mm-hmm. And that's a bay window, and then you don't see the light anymore. So all these spaces are spaces that air can move through. And if we don't have a good seal on the bottom, then the wind comes up and it goes through all those spaces. Now they insulate this plan by putting a blanket on the walls, and so the basement is conditioned. The thermal envelope goes all the way down. But if they just tuck that piece of fiberglass bat in there, it's not going to do a good job.
Right.
But it does a horrible job. Here's the electrical box they've cut the hole bigger than they need to. Will building paper or Tyvek, will that seal the hole? Sometimes sheathing's used as the air barrier, and we need to seal that. So let's go back to the one that, and I probably should move this slide. This is the one that we looked at before, that we had insulation up on the underside of the cantilever. And they've shoved a piece of insulation in there. And there's a piece of insulation you can see a little bit here, right? But we still have a void above. We have a gap above. So insulation just comes part way up. We have a piece of duct laying on it, and we have an airspace over the top. Well, the rim joist out there is not insulated. This is really a
I'm fascinated.
poor installation. If they had put the net on the bottom,
Yeah.
and maybe they would need to foam these a little bit or something, or put something to block it, or even put a piece of net over it, and then the loose blown insulation in there, we would have a much, much better insulation installation in that spot.
Yeah.
And we would be stopping the air moving above the insulation, because obviously we're going to have a lot of air movement above that insulation.
Where is the thermal envelope in this house?
Yeah. And that is, the thermal envelope then goes down the outside of the wall, around the outside of the cantilever, comes back in under the cantilever, and then because they're blanketing the walls here, it comes down to the basement floor. Now, when we get over here to the side, they're not spraying foam in the rim joists. They're just putting a piece of fiberglass bat. Now, they do ventilate these houses, so if they're controlling their moisture and they don't get excessive moisture, maybe we won't have any mold growth on that rim joist. But if they don't control the moisture, they have the potential for the same thing, because all it is fiberglass bat stuffed in the end of that rim. I don't think they'll end up with a mold problem like that one, but there's the potential.
Yeah.
So we have open air spaces. With that insulation compressed like that under the duct, we don't even have R8, let alone the R30 that's supposed to be in a floor system. I don't think the rim on the outside, that vertical piece, is even insulated at all. And the net and blow is probably the only really compliant method you could use on that. And then, of course, have a sealed air barrier on the underside of that surface. So here's a better, this is a good view that kind of explains some of those things I was trying to describe before. So this is a different house, but we have the same condition. We can see a bay is starting right here. Just to the left of these pipes from this side, if you walk around to the outside, the bay runs, The right side is the left side from outside, and you can see where the holes are there for that cantilever. Overcut hole there. If they don't seal that properly, we're going to have air movement. Again, we're going to have air movement through there. And you can see the little notches for the foundation bolts where the light's coming through.
Yeah.
Because this OSB comes down where we don't have a cantilever, those get covered or sealed from this plywood. Okay, the effects of airflow on energy efficiency. So we've been talking about how it's going to impact the airflow inside and outside the building. Now let's talk a little bit about the effect on energy efficiency. And we've touched a little bit on it, but obvious airflow increases air changes. The more airflow we have through our envelope, the more holes we have in it, the more air changes we're going to have every hour in our house. If our house is really leaky, then we might have an air change every hour. We leak all the air out of the house every hour, or every 2 hours, or every 3 hours. We want to get it down to where, it would be much less than that we don't leak all the air in the house, but every 6 or 7 or even 10 or 12 hours, we don't want to leak that much air.
Yeah.
Air infiltration, of course, increases with wind, and any air that leaks must be replaced. So if we have a lot of air leakage, we're going to have a higher utility expense simply because we're having to reheat air that we had to bring in, or cool air, hot air that we had to bring in. Mechanical ventilation, if we properly size it, people say, well, if I'm having to reheat, and we talked about this, if I'm having to reheat air for infiltration and ventilation, it's the same thing. Well, proper ventilation on a 3-bedroom house only requires like 60 to 70 CFM. It's not a lot of air, but we're bringing it in, we're getting rid of contaminants at the sources, whether it's in the bathroom or the kitchen, and we're maintaining it all the time. And so it doesn't cost as much because we might leak 5 or 10 or 20 times as much through infiltration that we bring in through ventilation. And we have, guess what? We have building science that gives us direction on how to properly size those. We need to balance and maintain our HVAC system, ensure ducts that are outside the envelope are sealed. But we also have to think about airflow, which doesn't increase air changes, but increases our energy cost. And you remember when we talked right at the first about the knee wall, the little short wall? If we don't have something on the backside, the air is just going to do this.
Yes.
And we're not leaking air in and out of the building through that, but we're losing energy because the insulation has air moving through it.
Right.
So here's a case where someone's prepared for that. We have a higher ceiling in this area, and on the other side of this blue board is attic space.
Okay.
So you got that?
Yeah. From one
And
of your
so what
beginning
they've done is they've come in and they've put that blue board on the back side. They will insulate it, and they can do bats or blow insulation. But once you insulate it and then you drywall this side, what happens to the insulation in there? It's enclosed on 6 sides. We got a block there, we have a block on top, we have the stud on that side, we have the blue board on the back, and we have the drywall on the front. And so what happens with that insulation? We have no air doing this, so we have the full effect of the R value. It resists the flow of heat through there. The insulation can do its job.
Right.
If we don't have the blue board and they just shove up the fiberglass, then we're going to have this convective flow. We're not moving air through it, we're moving it through the insulation, and we're increasing our utility expense, our energy consumption. So any place that we have drop ceilings or anything that creates an open cavity, we need to seal it up, otherwise we're going to have reduced R value.